Hello everyone. So last time we gave a quick review of pre-calculus. Last time, pre-calculus review. So basically we looked at the concept of functions, which we need in this course and many other courses, and different types of functions, one-to-one functions, invertible functions, graph of a function, exponential functions, logarithms as the inverse of exponential function, and piecewise functions. And we also looked at trigonometric functions and trigonometric identities, etc. So now today we want to start the concept of limit. So 1.3, the limit of a function. So let's see what the meaning of a limit is for a function. So given a function, so first of all, we need to have a function. And let's say x equals a inside domain of f, we know that f of a gives the output if the input is x equals a. So if the input is x equals a, then f of a gives the output. This is what you learn in pre-calculus. But now what about if the input is not exactly a, but instead is close to a? So in other words, we already can find the behavior of the function at a given point by just finding f of that point. But what about if you want to, if you're interested in the behavior of a function close to a given point, not just at the point, but close to a point? Then that's where the concept of limit will appear. So the limit of the function f determines the behavior of f close to, or if x is close to, the input x close to a fixed value a. Note that x equals a does not have to be in domain of f. Okay, so you can compare these two columns. In this one, when you want to find the behavior of a function at a point, so first of all, this point a has to be in domain of your function, and then you can find f of a gives you the output at the point. But here, we have a fixed value a, does not have to be in domain, and the x value is just close to a, and we want to know the behavior of f close to that point. So what do I mean by behavior of f? Well, I mean, like, for example, how large are the outputs? Are they, for example, let's say if x is close to 2, are the outputs close to some fixed point, let's say 5, for example, or are they just going to infinity, getting larger and larger? What happens to them? So we'll see many examples with graphs, but first I want you to know about the concept of limit. So limit of a function, the concept, very important concept that we used if the x values are not just they are not some fixed point A, but they're close to some fixed point A. So you may say, okay, what is the point, or what are the applications in practice? For example, when do we need X to be close to a point? Why don't we say X is at a point? So for example, we'll see later that, so there are many applications for limits and derivatives. Derivative itself is a special case of limit. But for example, let's say velocity. If you want to look at velocity of your car at, for example, at some specific time, let's say t equals 2 p.m. So you will see that you need to know the position of your time when t is close to 2, very close to 2. You need to know the positions, and then that way you can find the velocity. Okay, so this concept will appear naturally in many fields such as physics and many other fields, like I said last time, biology, economics, everywhere. So let me sketch a graph of a function for you. So consider function f with the following graph. Let's say this is 1, and let's say this is 2, and let's say this is 4. So here, this 1, I want to consider my A to be 1. This A that we talked about it here, you can take it as any number. Here we can also take A as any number. But let's say if I take my A to be 1. So set A equals 1. So when I set A equals 1, then like we said, we can consider two different things. One is the value of the function at the point. One is the behavior or the values of the function close to a point as x gets closer and closer to that point. So the value of function at the point, it's very straightforward. So set A equals 1, then f of 1 is how much? So how much is the output? F of 1 means the output if the input is 1. How much is the output if the input is 1? When we look at the graph, well, if input is 1 means here and along this vertical line, but we have one point here which is 1 and 4. So along this vertical line, if the input is 1, then the output is 4. So f of 1 is 4. So at the point, the output or the value is 4. But what about if the values of x or the value of x is not exactly 1, but just close to 1? What happens to the outputs in that case? Next, consider the case where the value of x is getting or the values of x are getting closer and closer to 1. So not equal to 1. If it could be equal to 1, but we already said what happens if the value of x is exactly 1. Now, in the next case, we want to consider a case where the value of x is not exactly 1, but just getting closer and closer to 1. So the notation for this x approaches to 1. This means x gets closer and closer to 1 from either side. So when you say closer and closer, because the x has two options, x can approach to 1. If you want to get close to 1, you can approach 1 from left or from right. So your x values could approach 1 from here or could approach 1 from here. So either case is possible, from left or from right. So x approaches to 1 means x gets closer and closer to 1, either from left So from left means, say, for example, it could be 0.9 or 0.99 or 0.999, etc. Or from right, say 1.1, x equals 1.1 or 1.01 or 1.001, etc. Okay, so x gets closer and closer to 1 from either left or from right. This is the mathematical notation. You can read it as x approaches to 1. And you want to know what happens to the outputs, what happens to the f of x values. Are they also getting closer and closer to some fixed point or no? As x gets closer and closer to 1, what happens to them? The next classical case where it is. So in this case, f of x values get closer and closer to which value? Let's look at the graph. Let me show you. See, if x is, for example, a little bit, if x is approaching to 1 from right, let's say if x is, for example, 1.1, look at the output. The output is very close to 2. Now, if x is even closer to 1, let's say 1.01, look at the output. The output now is even closer to 2. And so on. So also from left, let's say 0.9. See, the output is close to 2. Let's say 0.99. Output even closer to 2. And so on. So whether x is getting closer and closer to 1 from left, like 0.9, 0.99, 0.999, and so on, then the outputs get closer and closer to 2. If the x value is getting closer and closer to 1 from right, like 1.1, 1.01, 1.001, and so on, then the outputs get closer and closer to 2 again. Right? So it's here and then here and then here. So from either side, left or right, as x gets closer and closer to 1, the outputs get closer and closer to this value, which is 2. So in this case, f of x values get closer and closer to L equals 2. So in this case, we write limit f of x as x approaches to 1 equals 2. Okay? So this is a mathematical notation. Limit f of x as x approaches to 1 equals 2 means as x get closer and closer to 1, the outputs get closer and closer to 2. So let me write here. I call this one informal definition of limits. Let f of x be a function and x equals a be a fixed point. We write limit f of x as x approaches to a is equal to L if the outputs f of x get closer and closer. L as x values get closer and closer to a, either from left or from right. Okay, so this is called informal definition of limits. Limit f of x as x approaches to a equals L means the outputs get closer and closer to L as the inputs x get closer and closer to a. Now, why are we calling this informal definition? We're calling this informal definition because when we say closer and closer to L as x gets closer and closer to a, this word closer and closer must be, given, a definition must be given to it, and it has to, we have to make it strict, right? So what is the meaning of close, in other words? Because in mathematics, we want everything to be strictly defined. So for example, in the daily life conversation, I can say the weather is now cold. But in mathematics, we have to define what a cold temperature is. What do we mean by cold? Is it colder than, for example, 10 degrees or colder than 5 degrees? It has to be strictly defined. Everything in mathematics has to be strictly defined when it comes to the formal definitions. Intuitively, yes, it's okay to say, for example, 6 degrees is cold. But if you want to talk formally or precise proof or definition, everything has to be made strict. What is the meaning of cold? What is the meaning of warm in the case of weather? But here in the case of functions, we have to specify what close means. And what is the meaning of getting closer and closer as x get closer and closer to a? These have to be made strict. Yes, the strict definitions must be given for them. So that's where we want to talk about formal definition of limits. Normally in calculus, we don't cover that topic, but if you're interested, you can take analysis course, Math 225, and where we cover the formal definition of limits. Let me give you, so I gave you an example with the graph. Let me also give you an example with the formula. Normally, in this course, most examples or exercises are either dealing with a formula or with a graph. So normally students prefer formulas that they know how to work with them, but graphs a little bit tricky. So I suggest that you do lots of practice and do lots of exercises with graphs so that you get comfortable with graphs. Okay, so let's look at an example. Let f of x equals 2x plus 1. Find limit f of x as x approaches to, let's say, 2. So what is the meaning of this again? This means as x gets closer and closer to 2, what happens to the outputs, or what happens to the f of x values? So we can check, so x must get closer and closer to 2, either from left or from right. So from left means if x is a little bit less than 2, like 1.9, 1.99, etc. What happens to outputs? From right means if x is a little bit bigger than 2, like 2.1, 2.01, and so on. What happens to the f of x values? So from left, so let's say x equals 1.9. How much is the output? F of 1.9. 2 times 1.9 plus 1. So this is 3.8 plus 1, so that's 4.8. Or 1. Let's say 99. F of 1.99. 2 times 1.99 plus 1. So this is 4.98. And so on. Now let's look at also what happens if x gets closer and closer to 2 from right, and then we can decide. So from right, let's say if x is 2.1, then f of 2.1 is 2 times 2.1 plus 1, so this is 5.2. If x is, for example, 2.01, f of 2.01 is 2 times 2.01 plus 1, so this is 5.02, and so on. You can, of course, continue this list from this direction. You can include 1.999, 1.99999, and so on. And from this direction, you can include 2.01, 2.001, and so on. Okay, now what happens to the outputs? Look at the outputs, 4.8, 4.98. You can look at it. So see, these are getting closer and closer to 5. Look at the outputs, getting closer and closer to 5 from this direction, and also from this direction, the outputs getting closer and closer to 5 as well. So from either direction, as x approaches to 2, the outputs get closer and closer to 5, and that means the limit is 5. So some people here make mistake. They think, for example, limit is 4.98. No, limit is not 4.98. Limit means the ultimate behavior. 4.98 is, yes, one of the outputs. But what is the ultimate behavior, ultimate goal? So see, it's first 4.8, then 4.98, then 4.998, then 4.9998. So yes, each of these are outputs, but ultimately, these outputs getting closer and closer to 5. Same thing here, 5.2 is one output, 5.02 another output, 5.002 another output. Yes, each of these are output, but what is the limit, the ultimate behavior, ultimate goal, ultimate destination? So 5.02, 5.002, 5.00002. Ultimately, they are getting closer and closer to 5. So the limit here is 5. So since the outputs are getting closer and closer to 5, in either x approaching to 2 from left or right, we can say, or we can write that limit f of x as x approaches to 2 is equal to 5. Okay, so this is the meaning of limit. Now, one notation I want to talk about here. So here in this example, you saw that x could approach the number from right, means a little bit bigger than the number, or could approach the number from left, means a little bit less than the number. So we have a separate notation for each of these cases, x approaching to the number from left and from right. So let me tell you this notation. Notation. So x approaches a from right. So this one read x approaches a from right. Means x is getting closer and closer to a, and x is bigger than a. Similarly, x approaches to a from left. So again, this one read x approaches to a from left. Means x is getting closer and closer to a, and x is less than a. So in this example, above, so we can say that the limit f of x as x approaches to 2 from right was 5, and limit f of x as x approaches to 2 from left was also 5, and the whole limit was also 5. Right limit was 5, left limit was 5, the whole limit was also 5. So what is the connection between the whole limit and the right and left limit? So So in this example that we saw, all of them were 5. The right limit and left limit, they were both 5, and that means the whole limit is 5. So if the whole limit wants to be 5, that means x, when x approaches to 2 from either side, either right or left, the outputs must get closer and closer to 5, which means that right limit and left limit, both of them must be the same number. So this is always true. If the right limit and left limit, both of them exist and are equal to the same number, then we can say that the whole limit is also equal to the same number. But if either right limit or left limit do not exist, or if they exist but they are equal to the different numbers, then in that case, we say the whole limit does not exist. Because when we talk about the whole limit, that means x approaches to a number either from right or from left, meaning that x is a little bit bigger than the number or a little bit less than the number. Right? Now, if x is bigger than a little bit bigger than a number, the output's getting close to some number, but x a little bit less than the number, output's getting closer to another number. Then that means the whole behavior, when we consider the whole limit, the outputs do not get closer and closer to any fixed number, because from right is one number, from left is another number. So the whole behavior, there is no number if you want to consider the whole behavior of the function. Okay, so let me tell you about the connection between right limits and left limits and the whole limits. Okay, so if f of x is a function, so this one we can write it as a theorem. If f of x is a function, then limit f of x as x approaches to a is equal to L if and only if limit f of x as x approaches to a from right is equal to L, and limit f of x as x approaches to a from left is also L. So from this theorem, thus we can conclude that if the right limit, let's say, does not exist, or if the left limit does not exist, the DNE means does not exist. DNE, or if left limit does not exist, or if right limit is not same as left limit, then we can say that the whole limit does not exist. So the whole limit does not exist can happen in any of these three cases. If the right limit and left limit are not the same, or if one of the one-sided limits do not exist, or of course if both of them do not exist, again we can say that the whole limit does not exist. If both of them do not exist, of course the whole limit does not exist. If even one of them does not exist, the whole limit does not exist. Or if both of them exist but they are not equal to the same number, right-sided limit and left-sided limit, then we still can say that the whole limit does not exist. Okay, so let's look at an example. Consider a function f, where the function f with the following graph. So let's say this is 1, and let's say this is 2, and let's say this is 4. Find the right limit at 1 and left limit at 1 and the whole limit at 1. So how much is the right limit as 1 at 1 means if x is getting closer and closer to 1, a little bit bigger than 1, for example here or here. Look at the outputs. So for example here, the output is close to 4, this one even closer to 4, this one even closer to 4. So as x get closer and closer to 1 from right, a little bit bigger than 1, then the outputs get closer and closer to 4. So this limit is 4. The right limit is 4. So here, limit from x approaches to 1 from right is 4. Because the outputs get closer and closer to 4 as x approaches to 1 from right. Similarly, what about the left limit? Left limit means if x is a little bit less than 1. Close to 1, but a little bit less than 1. So for example here, see? Look at the outputs. Outputs get closer and closer to 2 this time. So for example, you're here and then you are here, right? So the outputs get closer and closer to 2. So the left limit is 2. So we can conclude that the right limit and left limit are not the same. And therefore, this means that the whole limit does not exist by theorem above. The theorem above is said that if one-sided limit does not exist, or if they both exist but they are not equal to the same number, in either case, we can say that the whole limit does not exist. This was an example with the graph. We can also, of course, do an example with a formula. So let's say example, let f of x equals, let's say, 2x plus 1 if x is bigger than or equal to 2, minus 3x minus 4 if x is less than 2. Find limit f of x as x approaches to 2 from right, and limit f of x as x approaches to 2 from left, and the whole limit. So from right, so this is limit 2x plus 1 as x approaches to 2 from right. So we can check that this is 5. We already did this, I think, in one of the examples before. We checked that the whole limit of 2x plus 1, whether x approaches to 2 from right or from left, is 5. So if the whole limit is 5, of course, each one-sided limit is also 5. So see examples above. And similarly, you can check that the left limit, similarly, check that the left limit is, how much is it? Minus 3 times 2 minus 4. This is minus 10. So what can we say? So left limit is minus 10. Right limit is 5. So you may wonder why to find the limit. So here 5, note that to get 5, you just need to replace x with 2 and you get 5. Here also I am replacing x with 2 and I get minus 10. So you may wonder why I'm doing this, or are we always allowed to just replace x with a number? Because remember, the whole idea was that, but we have two concepts. One is the value output of the function at a point, and at that case, of course, I have to replace x with a. But the other concept was the value of the function close to a point. So are we still in the second case? Are we still allowed to just replace x with the number like what we did here or here? So I'll answer this question later. Not always. Not always. We cannot always just replace x with the number. But for simple functions, we'll see that we're allowed to do that. So this one, I'll tell you later why we are allowed to replace x with a number. But for now, you can find the limit similar to what we did for here. Just use some x values. Here, for example, we use x equals 2.1, then 2.01, and so on. And we looked at the outputs that are getting closer and closer to 5. Here also, if you use the x values a little bit less than 2, so see, because if x is less than 2, the formula for f of x is minus 3x minus 4, right? So that's why I wrote minus 3x minus 4 here. You can also write that this is the limit f of x as x approaches to 2 from left. If x is less than 2, I have to use this formula. So this is the meaning of piecewise function, right? If x is bigger than 2, this is the formula. X less than 2, this is the formula. And then minus 3x minus 4 is my function. So I used it for x less than 2. And then I told you later that for simple functions, to like polynomials, to find the limit, you can simply replace x with the value. Well, I did that. I got minus 10. So right limit is 5 here. Left limit is minus 10. So right limit is 10. Left limit So right limit is 5 and left limit is minus 10. So that means right limit is not same as left limit. And that means the whole limit does not exist. Does not exist. Right limit and left limit, each of them exists, but they're not equal. So the whole limit does not exist. So for piecewise functions like this, normally at the point, at the border point, the limit does not exist. But only at 2 the limit does not exist. Of course, I can consider the limit at any other point as well. So for example, as an exercise, you can find let's say limit f of x as x approaches to, let's say, 2.2, and limit f of x as x approaches to 3, and limit f of x as x approaches to 1, for example. See, at 2, limit at 2 does not exist. But limit at, for example, 2.2. What is the meaning of limit at 2.2? Means x get closer and closer to 2.2 from either side. So from left, you could consider 2.1, or then 2.19, 2.1999, and so on. From right, you can consider 2.21 or 2.3 first, and then 2.21, right? And then 2 points. So see, here this is 2.2. If you consider, for example, 2.1, and then 2.19, for example, and so on, just get closer and closer to 2.2. From right, you could consider, for example, 2.3, or then, for example, 2.21, or then 2.201, and so on. So you can consider from left or from right some values, and then find the limit. You will see that the left limit and right limit are equal, and therefore the whole limit will exist in this case if x gets closer and closer to 2.2. Similarly, if x gets closer and closer to 3 from left or from right, you will see that again left limit, right limit are equal, therefore the whole limit exists. And similarly for x closer to 1, x approaches to 1 as well. Okay, so the limit of this function, although this is a piecewise function, the limit of this function at every point exists except at 2. 2 because it's a border point, the right limit, right behavior and left behavior become totally different. Then right and left limit are not equal at 2, and therefore limit does not exist at 2. But at any other point, limit exists. Okay. So this was the concept of limit, right limit, and left limit.